A research and policy-informed discussion focused on cross-curricular issues within science and mathematics. This presentation is going to focus on cross-curricular issues within science and maths, with a particular focus on measurement and statistics. The first question we need to consider is, what exactly do we mean by a cross-curricular approach to teaching and learning? And this is certainly no easy question to answer for the student teacher. Fogarty, in 1995, described 10 levels of curricular integration. So it is essential to have a clear conception of what we mean by cross-curricular. This presentation will be treating cross-curricular teaching as meaning the use of one subject in order to support the other. For example, using knowledge from mathematics, such as bar charts, to represent our findings in a science lesson about the varying lengths of shadows over the course of the day. This would allow the children to analyse and evaluate what they discover in their science lesson using knowledge that they have taken from maths. The reasons for adopting a cross-curricular approach to teaching stem from the constructivist theories of Piaget and Vygotsky. The idea is that children learn from their own experiences in a very holistic way. They do not compartmentalise what they learn into chunks. Therefore, a cross-curricular approach to teaching better reflects not only the holistic nature of reality, but also of how children learn. Carr goes on to say that knowledge is itself holistic, and that discrete subject teaching not only paints a misleading picture of knowledge as descriptive, but it creates artificial divisions between bodies of knowledge. A cross-curricular approach to maths and science has further specific benefits. Maths and science are naturally intertwined. We need maths to quantify and make sense of much of what we learn in science. The new national curriculum describes maths as critical to science. Science also is crucial for allowing us to apply our learning from mathematics in a meaningful and tangible context. For instance, during my first teaching practice, I taught 2 math lessons on capacity to a Year 1 class. The first lesson focused on using the correct mathematical terminology, etc., and was very much a discrete lesson. The second lesson, however, I put in the context of a science experiment, with 4 different activities, each exploring capacity. The children would need to hypothesise which container could hold the most cubes, or how many out of a selection of counters would it take to either fill or half fill a container. This cross-curricular approach to the lesson worked incredibly well. It took the learning from the previous day and put it into a meaningful context whereby the children had to apply that learning to a practical task. The children responded fantastically to this lesson. They were well motivated, on task, and more importantly, enjoying their learning. This lesson really demonstrated the potential power that cross-curricular teaching can have on children's learning and motivation. A cross-curricular approach like this can be achieved throughout a child's primary school career. The working scientifically feature of the Science National Curriculum could be used in a whole range of maths lessons. We could, for example, in a Year 6 classroom, use a science experiment investigating how the brightness of bulbs is affected by the number of cells in a circuit to teach how to construct a line graph. And in science, the opportunities for using maths are endless due to the natural interconnectedness of the subjects. We can see that there are enormous pedagogical benefits to a cross-curricular approach between maths and science. Not only does it link strongly with the holistic way in which children learn, but it helps reinforce the natural interconnectedness between maths and science, particularly in relation to measurement and statistics, providing many opportunities for learning in one subject to be enhanced by the other. And from my own teaching practice, I have discovered that a cross-curricular approach can really create a stimulating and rich learning environment for children. However, there are drawbacks to cross-curricular teaching. The 3 wise men report acknowledges the constructivist view that children learn holistically, but it suggests that by not teaching subjects discretely, we would be depriving children of some of the most powerful tools we have for making sense of the world. Breaking something down into its constituent parts is an effective way of learning something. When we learn to play a song, first we learn the introduction, then the chorus, and then the bridge, as this makes it easier to learn than just trying to learn the whole song. And so the same is true of children's learning. By breaking subjects down into maths and science, etc., we are making it easier for children to make sense of the world. Hayes furthers this by arguing that In order to learn, we need the delineated boundaries provided by discrete teaching so as to ensure that children are gaining the fundamental skills required in each discipline. He states that cross-curricular teaching is insufficiently rigorous in doing so, and I'm reflecting on my own cross-curricular teaching. Without my initial discrete mathematical lesson, the children may have missed the fundamental outcome of the lesson, that is, to grasp the key terminology of capacity, and they may have focused on the practical scientific nature of the lesson instead. What this teaches us is that discrete teaching also has its benefits. It provides children with an adequate and stable knowledge of each subject. It also provides children with very powerful tools for making sense of the world. A further issue with cross-curricular teaching is our own subject knowledge. Making links between science and maths requires us to have good subject knowledge of both subjects so that we are able to make those links when teaching. Plowden in 1967 and Alexander in 2010 acknowledged that any attempts to form connections between subjects could actually prove detrimental if the teacher doesn't have sufficient subject knowledge to do this. Stinson et al. Also suggest that our confidence in teaching maths and science may prove detrimental to making cross-curricular links if we do not feel confident teaching those subjects. In conclusion, we can see that there are definite pedagogical merits to both discrete and cross-curricular approaches to teaching. But we can agree with Rennie et al. And the Rose report that we should aim to strike a balance between the two. For example, if teaching how to construct a line graph, we should teach it first in maths discretely, and once the children have grasped the fundamental principles, then this learning can be used to support a science lesson. This balance would see us establish new learning discretely and then embed that learning in a relevant and meaningful context by using it in a cross-curricular lesson. This balance, however, must take into account our own limitations as teachers in terms of both our subject knowledge and confidence in teaching maths and science. If we are not confident teaching electricity, this may not be the best opportunity to embed learning about graphs. So while a balance would be ideal, we also have to be realistic about how much of a balance we can achieve, and this will vary from teacher to teacher and from school to school. One way we could achieve this balance would be to introduce ICT to cross-curricular lessons. Sharp states that software packages such as Excel allow students to construct graphs without the tedious work of having to draw them out. So if we are using graphs in science, by using ICT, we can save a lot of time and allow children to focus on interpreting the graphs and their findings rather than drawing out graphs. The accessibility of tablets and the internet in school also allow children to access a wealth of information and interactive learning games. Online videos can bring experiments into the classroom that previously would not have been feasible, either due to timing, resourcing, or health and safety issues. So if we are using science to support maths, we have access to a wide range of online resources to demonstrate the meaningful context. Perhaps most importantly, children enjoy using ICT in the classroom and really engage when there is an opportunity to use an iPad or the digital camera to record their own work. And from my own teaching practice, I have seen that using ICT in the classroom can really motivate and inspire children to learn. Though there are huge pedagogical and pragmatic reasons for using ICT in the classroom, from my own teaching practice, I have not seen these benefits fully explored. I have found that iPads and digital cameras are predominantly used for recording for the purpose of evidencing in children's books, and not as tools to enhance the children's learning experience. I have found this comes down to teacher experience and confidence in using ICT. That where teachers aren't confident using technology in the classroom, it is used when it is needed, not as a tool for learning. To conclude, pedagogically, there are enormous benefits to striking a balance between discrete and cross-curricular teaching and using ICT in the classroom. But in doing so, we need to be aware of how pragmatic it is to do so, due to teacher confidence and subject knowledge. However, I think with continual professional development in subject areas and support from subject specialists, these barriers can be overcome and this balance can be struck, and we can begin using ICT to its full potential in the classroom.